Good evening, everyone. Let us get started. So, we have till now whatever we have discussed is finally we have looked into the field inside a DC machine, the field excitation. We have understood about the induced EMFs, how induced EMFs are quasi square wave, but because of the commutator and brush arrangement, they appear to be a DC quantity. Similarly, the field inductance and armature inductance, although they very weakly depend on rotor position, depending on the number of slots which are there in the armature, but the functions are the armature inductance as well as the field inductance are almost constant. Because of that, it is reasonable to assume them as constant numbers. So finally, what the dynamic equivalent circuit that we derived and understood how the dynamic equivalent circuit is the way it is. So this is the dynamic equivalent circuit. So this is the armature. I have indicated the brush as well. So the steady state equivalent circuit will only include the armature resistance, but it will also have the armature inductance because it's a dynamic equivalent circuit. We have the armature resistance as well. So this is our armature circuit where we have to apply some external voltage input, that is VA, and some current will flow because of that, and there will be some induced EMF, let us say EB. Now along with that we have the field winding also. So the field winding, we have understood why there is no induced EMF in the field winding. Induced EMF in the sense that there is no speed dependent EMF appearing across the field winding, and only the induced EMF is due to the inductance in the dynamic condition. So we have the field winding. If I try to indicate, uh, there is the field inductance and it has the field winding resistance also. So there is no back EMF term. So we have VA voltage that is applied across that field voltage. We have RF, the field winding resistance, and LF, the field winding inductance, and some current IF will flow. Now a motor, we have understood that it has a mechanical subsystem also. So the mechanical subsystem, so this armature that is rotating, so say it is rotating at some velocity, say omega. Now if it is acting as a motoring mode, then the electromagnetic torque that will be aiding that rotation, so electromagnetic torque will be in the same direction, and there will be some friction which will be opposing that, some frictional torque that will be opposing that, and that frictional torque, for a very simplified case, is proportional to speed. So frictional torque T friction is proportional to omega, and we can assume that so that is an assumption. It will actually depend on the type of bearing. Bearing, what is bearing? Bearing is any electrical machine that has a rotating part that is rotating it, and it has a stationary part. So say this internal part is rotating, and this our external part is so any machine has a rotor and a stator. The rotor is also needs to be supported in the stationary structure only. So we need some kind of a thing that is a interface between the stationary body and the rotating body. So we use something called as a bearing, and the most commonly used bearing is something called as ball bearing, where we have a structure like this, where the inner surface is connected to the rotor and the outer surface is connected to the stationary part, and there are some balls in between, and there is some lubrication put. So this is what is called as bearing, which is required in any rotating body. uh, to interface between the stationary part and the rotating part. So the frictional torque, that is mostly due to the bearing type. So depending on the bearing type, so most ball bearings up to some range of speed, the characteristic the frictional torque is proportional to speed. So the proportionality constant, if it is b, then the frictional torque is b omega. So this frictional torque, whatever I have indicated, that is that can be modeled as b omega. And there is something called as inertia that will that is due to the mass and structure of the rotating part, which will have some inertia that will stop any change in rotational speed. So inertia is something that opposes the speed. So say if the motor is running at omega 1, say the motor is running at omega 1, if I want to make the speed, say, ramp up to omega 2, then in this duration, in the steady state where speed is constant at omega, we need not apply any additional torque. Similarly, where whenever speed is again constant, we need not apply additional torque. But in the rising portion, you can understand that there will be some additional torque requirement, which will be required to raise the motor speed from omega 1 to omega 2. So in that duration, the additional torque that will be required, that will be needed to overcome the inertia. So inertial torque, so Ti, that is proportional to the inertial speed, that is indicated as J. So there is the moment of inertia also. So, and obviously the motor will be driving some load, so that will also be opposing the original motion of rotate or original direction of rotation. So we have total electromagnetic torque that will have to supply any change of rotation. So this is the inertial torque, the frictional torque, that is b omega, and it will also have to overcome the load torque. So this is the mechanical differential equation. So say uh, uh, say this is the number one equation. Then this first armature circuit you have already written. We have VA. If I write the KVL equation, then VA is equal to LA DIA dt plus RA into IA plus EB. So this is the second equation, let us say. And the third equation is the field circuit. So say VF equal to LF DIF dt plus RF IF. So this is the third differential equation for the field winding. And we'll also have something that will be relating the field winding and the armature winding. So back EMF is dependent on the field winding current, and similarly that current that is flowing through the armature, the torque generation, electromagnetic torque, that is also dependent on the field winding current, or indirectly the flux. We have understood before what do we mean by flux per pole from our previous discussion. So we know that the back EMF is proportional to the speed as well as the field winding current, and the proportionality constant, say it is K, proportionality constant is K. And again similarly, TEM, electromagnetic torque, that is also proportional to current as well as field current, armature current and field current, and the proportionality constant, if we do that, it will come out to be the same K. So we have another two sets of equation that is relevant for electromechanical energy conversion. So the speed, that is a mechanical quantity that appears across as the induced EMF in the armature circuit. So that is like mechanical is being converted to electrical, and electrical current, which is electrical quantity that is being converted to the electromagnetic torque, that is a mechanical quantity. So we have two more equations, which are these two. We have fourth equation and fifth equation. Now, what are the variables? What are the variables? What do you mean by variables? So, we'll understand the system, its definition, other things the system theory that will be required for going into control. We'll understand that in the next class, but to have a brief idea, any system has some quantities whose values do not change significantly. So those are called as parameters, and some quantities which varies over the operating range, they are called as the variables. Now in a DC machine, you can understand that the voltage that will not remain constant, that will be continuously varying, because you will want to change the speed or change the torque production. You want to supply or drive a higher load. So because of that, you will be changing the voltage, you will be changing the armature circuit voltage. If you want to change the excitation, you will be changing the field circuit voltage. Because of that, the current will also be varying, the field current will also be varying, the torque that is generated, that is also varying. The load torque may vary, because load torque may itself be speed dependent. The speed most important, that is also a variable. So the speed may also change. Frictional torque is again a dependent quantity on the speed. So frictional torque b omega, that may also change. So um, the back EMF, that is another variable that is dependent on the speed. So we have all these quantities whose values can change during the operating condition of the machine. So these quantities are called the variables, and among the variables we have some quantities which are like the user will be controlling them. User can control them or change them to get something desired. So those are like the input quantities or input variables. And something like speed is something that we'll be observing, and we may try to, when we are running a motor, we want the motor to run at a certain speed. So speed is like what we'll be observing, and that is like the output variable of the system. And also current is another quantity that we can measure them. We can measure the current. So that is also like output quantity, which we may not, so indirectly we may need to, um, we may want to sense the current and do some control to, so that the current is at some value and we get certain torque. So in these equations you can understand that we have the VA, VF, which are like the input quantities or input variables, whereas the speed is the direct output variable. And we have some intermediate things like the current, which will be indirectly, which will be causing the torque, electromagnetic torque, and that in turns will be deciding the speed. So we have some intermediate variables like the currents. uh, if I can bring in that, flux linkage is also one, like the field flux per pole, that is also a intermediate quantity, which is whose information is actually there. The flux is nothing but inductance into current, that is the flux linkage. So we have that information inside this, as so that flux is actually assumed here to be proportional to the field current. So field current is another variable for us. But you can see that there are certain quantities whose values do not change with time. So what are those variables? We have we have, say, we have, for the second equation, to start with the armature circuit, we have the armature winding resistor, armature winding inductance. We have seen what is armature circuit inductance, how does it change with rotor rotation. But we have seen that the dependence of La with rotor position is quite weak. So for all practical purposes of analysis, this La can be, the variation in La is quite negligible, and it is a quantity whose value do not change largely with the motor rotating. So La is one of the parameters of the system whose value is a constant here. So second parameter that we have is the armature circuit resistance. Again, any winding, any coil that has some resistance rho into L by A, the depending on the length of the wear, depending on the cross sectional area of the wear, and the rho, that is the resistivity value, reasonably remain constant. So that means if the winding length and cross sectional area is fixed, so resistance mostly remains fixed. But that is also not strictly true, because any resistance that is current dependent, and with current will change the temperature, and temperature will change the resistivity of the material slightly. So strictly speaking, again, this resistance, armature winding resistance, that is like resistance, armature winding resistance, that is in some way a function of the current itself. But uh, for all practical purposes, or because for this analysis purposes, we will see what is the desire, what difficulties may come in if we try to model these variations of RALA, that will overcomplicate our model. So we will also see the implications of that. And because it is largely a constant quantity, so it also can be considered as or approximated to be a constant quantity. So this is the second variable. Along with that, similarly for the field winding, we have the field winding inductance and field winding resistance are the two parameters for the field winding. Again, for the mechanical subsystem, we have the moment of inertia J and the frictional coefficient B, which are the two parameters for the mechanical subsystem. And in the electromagnetic energy transfer, we have this constant K, which is another parameter of the system, which decides for a given speed and field current what will be the induced EMF, and for a given current, armature current and field current, what will be the electromagnetic torque. So if we go through the derivations, then we found, that is well discussed in books also, that this K, whatever relates the field, the induced EMF to current, multiplication of current and field current and speed, and the K that relates the um, torque to multiplication of armature current and field current, uh, they are, their units are different, but quantitatively that number is the same. So I have indicated them, these two, as the same constant number K. Now if we want to do any control, it is important for us to know the values of these parameters approximately up to some accuracy. We may not, so it is not possible to know these values exactly, because as I have indicated, there is some variation of these values with temperature, like the resistances will vary with temperature, and temperature depends on the current that is flowing through the wires. So uh, those are not a constant quantity, but we need to know some approximate values of those resistances. Similarly, we need to know some approximate values of the inductances. We need to know some approximate values of the moment of inertia and frictional coefficient, and also we need to know some approximate value of this K. So what we will be discussing in today's class is, say you are given a DC machine, a physical DC motor. You do not know the design, you do not know anything about the motor, but you are supposed to do some controls, as some inner loop current control, outer loop speed control. So some speed control DC machine you want to run. So for that, it is important for you to know the parameter values, like all the parameters which I have encircled, the LA, RA, LF, RF, JB and K. So total we have 7 parameters. You need to know the values of these 7 parameters if you want to do any control. So in today's class we will be discussing how you can do some experiments and find out what are the values of these parameters, right? Any question till now?
No, sir, it's clear.
Okay, so let us get started with the resistances. So resistance finding is easy, quite easy. So what you have, say you have a machine. So say this is your DC machine, which has some base, and that is fixed in a stationary reference frame that has shaft, and say it may be coupled to something else. So say you need to run some other load, say pump load or something. So that is also there. It also has some base, and that is fixed to the ground. So this is like the load, and this is like your motor, right? Okay, I should have extended the shaft a little bit, but anyway, it's fine. So we have the coupling and we have the load connected, right? This is the system that we have. Now electrically speaking, what do we have? We have say one set of, so there is the rotor. Say rotor has some so there is some brush connected, and there is the commutator segments also. So from brush, two terminals are coming. So these two terminals are the armature terminals, and also in stator we have two other terminals. We have the field winding terminals. So say some winding field winding is there, whose two terminals are accessible to you. You have the field winding terminals, right? So you have, electrically speaking, you have four terminals at your disposal. Now first thing is, suppose nothing is written, can you identify among these four terminals or the two windings, which one is the armature and which one is filled? That is the first task. Any idea? So whatever we
Based
have
on the
discussed.
time constant, we can
No,
choose
no, we
by
have not. We
giving
have not. We are yet to do any experiments. You have to identify which one is. Suppose you just have to identify by observation which one is filled, which one is armature. How do you do that? Which one needs to have higher current?
armature.
So the armature current and field current, if I compare, armature current is typically quite compared to field current. Now if you want to pass some bigger current or a higher amount of current through a winding,
The cross-sectional area based on cross-sectional area.
the cross sectional area, the armature winding wears will be quite thick. So if you do some inspection, you will be able to find out that uh, this armature winding, the cross sectional area will be quite thick. So it will be a thick conductor, whereas the field winding, because it only needs to carry some small ampere of current, typically lower than 1 ampere mostly, in most cases 1 ampere, 2 ampere, something like that, not a 0.5 ampere, typically lower than 1 ampere. So you will, if you just simply compare, you will be able to, by inspection, you will to find out that okay, this is armature winding, this is field winding. Okay, now suppose you want to first measure the field winding resistance, and then followed by armature winding resistance. What you can do, you can you can have a DC. So suppose you have some nameplate rating it mentions that field winding rating is 220 volt, say 1 ampere. So this is the rating, of the field winding. So from here to, by calculation also you can understand, because field winding, if you are supposed to give constant voltage, and it is the current will be constant. So by these ratings also you can find out that field resistance will be is 220 ohms, but it may not be exactly the same number. So if you want to find that experimentally, what you do is you connect a DC source, say a variable DC source, say you connect a controllable variable DC source, so some VF, so that you can apply some voltage. You keep the armature winding open, you keep the other things unexcited, nothing except than uh, this field winding. Now you go on changing this field winding voltage, and you measure the current. You connect some ammeter and you keep on measuring the current. Now if you vary, so it is generally recommended that you pass the full current, that is 1 ampere, the rated current, for some time first, to start with, so that the winding becomes hot, so that you can measure, because when the motor is actually operating, the winding will be quite hot. And once you pass the same 1 ampere amount of current for some time, the winding will become hot. So you can start your measurement. Say you have the IF, which the one which you are measuring, and you have the voltage which you are setting to make that much amount of current flow. So say you start with 1 ampere, you make 1 ampere current to flow for some time by applying some voltage. You know some voltage is required and some current 1 ampere, say that much you have passed. So you get the first point. Now you reduce the voltage little bit so that current becomes a lower value, and you measure that current, you get the second point. Similarly you get third point, fourth point, fifth point, and zero obviously will that is not a point. So zero voltage, that is not an experimental point, so I should not uh, I should not um, include that as one of the experimental points. You don't know how much, if you open it, then no current flow, so you never know what is happening there. So but you have these experimental points of different for different currents, right? Now mostly you will find that it will be, if you take a few readings and take the average of them, then you will find that it will be a straight line passing through the origin, right? You will find that it is a straight line passing through origin, and if you calculate its slope, then the slope is nothing but 1 by Rf, that is If by Vf. So delta If by delta Vf, that is the slope of this line, and that is nothing but the reciprocal of the field winding resistance. So this is how you can find the field winding resistance. And one thing is, because uh, you have to pass the same amount of current, so you need some voltage supply, that can supply some voltage up to the rated voltage. So 220 volt, you need some voltage supply that can supply up to 220 volt, right? So this is how we can get the field winding resistance. Now let us come to the armature winding resistance. So say armature winding resistance, the armature winding coil rating reads like, say, 220 volt, 20 ampere, something like this. So 220 volt is the rated armature voltage that you are supposed to uh, supposed to connect. And in the rated condition, that is when the motor is supplying the rated torque, then 20 ampere is supposed to flow through the armature winding, and the motor is rotating at the rated speed. So that is the armature winding. Now what do, you keep, now that is the second set of experiment to get the field winding. So you keep the field winding open, you do not want the motor to rotate, so you Now take away the excitation from the field winding. You connect a DC source, sorry, you connect a variable voltage DC, you connect a variable voltage DC across the armature. Now one question, so for the field winding, the voltage for testing whatever voltage source we have taken, that needs to be up to the rated. Now for this case, what do you expect? How much should be the voltage we, if you want to apply, what do you think? Do you need 220 volt to pass 20 ampere of current through this winding, or for by inspection of this can we just write that armature resistance will be 220 divided by 20, that is uh, how much is that, 11 ohm? Can we write that for this case? Yeah, I told that it can be 220 by 1, that is 220 ohm. I told that is also one of the ways, but experimentally finding out needs these experiments. What do you think about the armature? Can I write 220 by 20 equal to 11 ohm as the armature winding resistance straight away?
Sir, I think we cannot because based on the load, the current changes for the same 220 volts.
No, when, so this rating is about the rated condition. That is, the motor is rotating. If we apply 220 volt and the motor delivers the rated torque, then the current is supposed to be 20 ampere. So can we write 220 by 20 equal to 11
Sir,
ohm
also
as
like
the,
when overload occurs, the current draw.
when
Hello, sir, can you
come
hear
again?
me? Sir,
Yes.
like when the motor is overloaded, so it draws more than 20 amps. So in that case, the
No, no,
resistance will be less than 11
forget
ohms.
about
So we cannot
overloading.
say.
Forget about overloading. Forget
Okay,
about
sir.
overloading. We are not overloading the motor.
Um,
Let me go back to the armature circuit.
Sir, based on the EMF, the speed, the back EMF changes.
Yes. So when there is some induced EMF, when the motor is rotating, there is some induced EMF across the two terminals of the motor. So it is not that 220 volt is required to flow 20 ampere current through that winding alone. When it is rotating, there is some significant amount of induced voltage that can be as high as 200 volt, 210 volt, depending on the design and other things. But in the armature winding, whatever voltage is required, the significant amount of that actually goes to oppose the back EMF. So for armature winding, we can never straight away write the rated voltage by rated current is equal to the armature winding resistance, right? So that is the point. When motor is rotating, armature winding, the rated condition, these ratings are for the operating condition when motor is rotating. Motor rotating and field winding excited means there will be some back EMF. So the most of this armature voltage that is required to oppose that voltage. Suppose you have a motor that has some back EMF of 200 volt, and you have some resistor, you have some winding, and you want to pass some current 20 ampere through it, and say it has some resistance of 1 ohm. Now how much voltage will be required? It will be 200 volt. The voltage VA has to be higher than 220 volt, 200 volt, so that the current goes in this direction, and it has to oppose the resistive drop across the armature winding also. So the resistive drop across the armature winding will be 20 volt, so the total voltage required will be 220 volt, right? So that means that uh, armature voltage, armature winding, the rating The significant amount of that voltage is actually required to oppose the back EMF. Okay. Now let us try start doing the experiment. So that means when we are doing this experiment for this armature, the voltage source that could be quite low, because now the motor is not rotating, we are not exciting the field, so that means there is no flux, so there will be no torque production. So the even if we excite the armature and some current flows up to 20 ampere or even higher than that, there will not be any torque production and the motor will not rotate. So let us start doing the similar exercise that we have done for the armature winding. Doing uh, let us try doing that for the uh, armature winding also, whatever we have done for the field winding. So in this case also, what we will be doing is will be measuring the current and will be exciting with some voltage. So here also we will change the voltage so that the ammeter reads about 20 ampere. So first will make 20 ampere current to flow for some time, so that the winding becomes hot, and current flow and temperature, they are not simultaneous quantities, because you need some time to for the winding to get hot. So you will have to wait for some time so that the winding becomes hot, say 1 to 2 minutes, 5 minutes, whatever small amount of time. uh, so after that, you measure whatever the voltage you have applied, and you have 20 ampere of current, whatever amount of current that is flowing. You take the first experimental point, then you reduce the voltage by some amount, you measure the current, you reduce the voltage by some amount, you take multiple readings. You take multiple readings like that, very close to y-axis. You may not be able to read very accurately. So uh, that is why I have, let me say, let us say I stop here. That is the minimum current that I can, the my ammeter can measure accurately. So say this is the armature current versus voltage characteristic that I have obtained. Now typically, if you join this curve, then again you are supposed to get a constant a straight line. uh, so the slope will be the constant. But what typically happens is this, unlike the field winding, this does not pass to the origin. If you extrapolate it back to the left hand side, you will find that there is some y-axis intercept. There is some y-axis intercept that is, oh sorry, I've just uh, drawn it the, so yeah, this is also true. If I just change the axis level, or that I should not do. So let me redraw it once more. I'm coming to the point why there will be a x-axis or y-axis intercept. So the experimental method requires IA and VA, and if you do some experiments, you will find that, yeah, you get some experimental points like this, and if you join them, you will see that there will be most possibly some x intercept. So that means the this resistive drop, whatever resistive drop is happening in the armature circuit, that is not purely a resistance. It is like some constant voltage plus some resistance. So this characteristic, if you want to uh, describe or write a equation for this, you cannot like this characteristic. If you want to write, then you can write that if by vf the ratio is a constant number, which you know that is a reciprocal of the field winding resistance. So the equation is like if equal to 1 by rf into vf. So this is the straight line equation for the field winding case. But in this case, if you want to write the equation, you will have to write it like y equal to mx plus c. So say the slope, you get some slope that is equal to 1 by ra, that is actually the field winding or the armature winding resistance. So that is the slope. You have the x-axis variable, that is va, and along with that you have some intercept. You have some intercept y equal to mx. So you will have some negative one, so um, you will have some, say, a constant quantity, say v0, right? You will have some voltage. So this is nothing but v0, the x-axis intercept, say it is some v0. So the equation that finally comes out is va equal to I or RAIA, uh, okay. So I think I have something is there, some mistake is there here. So if I if I so v0 meaning can be something else. So this is some v0, forget what that is. So va is iara plus some ra into v0, right? This is the equation that you have. Now this ra into v0, that happens to be a constant quantity, right? So you if you see this, the equation, steady state equation for this one, you have va, some voltage that you are applying. Part of that is going as the IR drop, and another part is going as some constant voltage drop that is not very strongly dependent on the current, right? This ra is a constant and vo is also a constant. So this overall thing is a constant. So what is this constant quantity for? That is actually due to the brush drop. So you have the commutator segment and the brush. The brush is typically made of a carbon thing. So the brush contact drop, the brush contact voltage drop, it is seen that that is that is not very strongly dependent on the current that is taken that flows to the winding, but that is a constant quantity, mostly independent of the amount of current that you are drawing. So this constant quantity is typically written as the vb, that is the brush voltage drop, and typically ranges from say 1 to 2 volt. So if you remember your numerical problems, you may remember that brush voltage drop is typically given as 1 volt, 2 volt, 1.5 volt, typically in that range. And the brush voltage drop also you can find out, also will not but we will not include that, because this small brush voltage drop 1 volt or 2 volt, that is quite insignificant compared to the 220 volt of supply or the significant back EMF that we are giving. But when you are calculating the power loss, that some significant power loss happens in the brush contact. So during power loss calculation, it is important to take care or consider this brush voltage drop also. So this is how we can get the armature and field winding resistances. So for field winding resistance, we open the armature, we pass some current, rated current up to some time, then we reduce the voltage and reduce the current. We draw this plot, we we join the lines, we find that typically it is a straight line joining, going passing through the origin. Whatever is the slope, that is 1 by Rf, that is the field winding resistance. So you get one of the parameters. And for the armature circuit, we understood that why we require lower amount of voltage than the rated one. When we are doing this kind of a test, we are not exciting the field, will just excite the armature, will pass the rated amount of current to the armature for some time so that it becomes hot. Then we'll start taking reading. The first point is the rated current, then we reduce the voltage, current reduces, we take certain readings, we join them by a straight line. Typically we find that there is some y x-axis intercept, and if we write down the equation for that, the first one, say Ia equal to, so this is y equal to mx plus c kind of a thing, y equal to mx plus c, where c is uh, so so this is uh, the equation of the straight line. Now if we try to get the parameters, m will be 1 by Ra, and there is some c, some intercept, so y axis intercept will be negative, so uh, some value, so whatever, say this is minus I0, so I should have actually written minus I0 to be consistent with the things. So this would have been Va equal to, so let me erase this one.
Sir, why we need to go for maximum current and there we are staying for a
so
longer
that
time so that it becomes
so that
hot?
the winding becomes hot, we get the hot resistance, because actually when the motor will be running, the current, there will be some current flow, there is no use of getting the cold resistance. Machine never operates there. When machine operates, the winding will be always hot, so it is meaningful to get the hot resistance rather than the cold resistance.
Okay, sir. Thank you.
Okay, so this is the equation y equal to mx plus c, where c is the y-axis intercept, which is minus I0, as we get from by extrapolating this curve. So Ia equal to 1 by Ra, that is the slope, into Va minus I0. So if we rewrite this, then Va is equal to RAIA plus RA into I0. Now whatever RA into I0, RA is a constant, I0 is a constant, so this multiplication, that is another constant, that is typically defined as the brush voltage drop VB. So the equation becomes VA equal to RAIA plus VB, which is where VB is the brush voltage drop. So we found out everything. We found out the resistance, which we will be using, and will be neglecting the brush voltage drop for all cases other than power loss calculation. Now let us try to understand what can we do to find the inductances. Again we have the same setup. We have the DC machine, we have the load connected, we have the pump load connected, both of them are grounded, or they are fixedly connected to some rigid support. This is the motor, so this is the pump. We have two windings, this is the armature, so this is the field. So this is the armature, and we have the field winding, so we have two sets of winding. Now what can we do? We want to find the inductances. What can be done? Let us say we do not do anything to the mechanical side, we keep the field winding open, and we get some say we get some switch, and we get some DC supply, right? And we have some ammeter connected, or we have some, we probe it. We have to use TS, so digital storage oscilloscope, to see the waveforms. This is not a DC measurement, so the simple meters will not help. We need to get the waveforms. We need to probe some voltage probes here, So we will be measuring the voltage here, we will be measuring the current there. So in digital storage oscilloscope, we will be looking at the voltage as well as current in the armature winding as well as in the field winding. So say we turn the switch. So initially the voltage here, that is 0. There is no voltage because there is no induced EMF, because the motor is not rotating, the field is not connected. So the voltage initially that will be reading will be 0, and the current will also be 0. Right now we suddenly close this switch. As soon as we close it, the voltage will be like, there will be a step change in the voltage from whatever is the value, say v a, or say use some values, say 20 volt, 20 volt supply we are using. So there will be a step jump in voltage from 0 volt to 20 volt. Right now, accordingly what will happen in the current is, we will see that the current will not rise instantaneously, but it will rise and steady it down like this. It will be like a first order response, where the final value will be whatever, say 20 volt we are using. We already know the armature circuit resistance, so whatever is 20 by Ra, that will be the final value of current. Say it is 1 ampere, so let us say it is 20 1 ohm. So the final value may be 20 ampere, but it will take some time for the current to reach from 0 to 10 ampere, 0 to 20 ampere. So from this response, so this is expected to be a typical first order response, and the first order response is typically, say Ia equal to I0, that is the final value, and the response is 1 minus e to the power t by tau, where tau a is the time constant of the first order circuit. So here we know what is the final value, that is I0 equal to 20, 1 minus e to the power minus t by tau a. Now we have this Ia as a function of time. We have this equation. By fitting this, it is possible for us to find what is the time constant. What is the time constant tau a from this waveform? And tau a, we know, if we solve this thing for the armature winding, that is a series resistance and inductance, we know that tau is nothing but Ra by La by Ra. We already know Ra, so we know t tau a. So it is possible for us to find what is the La value is. Now the same experiment can be done for the field winding also. In that case, we will not excite anything in the armature. The armature is open. So the armature is open, but we do the same thing. We get a voltage supply, voltage source. We connect a switch. We connect it to the field winding. We probe it to get the current, say If, and we probe it here to get the voltage, say Vf. Similarly, if this is Vf and If, say we apply some 200 volt, 220 volt, what is the rated in step, and If similarly, there will be a step jump from say 222, so say 1 ampere, depending on the RF value. So final steady state value is well known, but there will be again a first order type of response. We by fitting that, we will get the tau f, the time constant for the field winding. By equation we know that time constant is equal to Lf by Rf, that is equal to tau f. Rf we know, tau f we know, we can find out what is the Lf. So that this is how we can get the field winding inductance and armature winding inductance. Now there is a second way of finding that also. So this one is like a step response, where we need some voltage supply, we need a switch, and we are turning on that switch. We are measuring the voltage and current. From current response, fitting it to a first order response, we can find out the time constant, and from there it is possible for us to get the um, inductance because we know the resistance. Now there is a second way also, which is like a sinusoidal excitation. So we have the motor, we have the pump, we have these things grounded, we have the armature winding, we have the field winding, right? We have these two windings. Now what do? We'll again keep one of the windings open. uh, then let us say we take some sinusoidal voltage source and we connect a we probe it to get the current. We connect it, we probe it to record the armature winding current, we probe it to get the field winding voltage, armature winding voltage, and we see them in oscilloscope. The voltage, let us say we see, so VA is some sinusoidal voltage like this. This is something like this in the oscilloscope. And the current, because it's a inductive one, it will lag the current will be lagging the voltage by some amount. It will be lagging the current, lagging the voltage by some amount. So let us say we get some waveform like this of current, right? Now, so this is the current VA and IA. These we can see in the DSO, the digital storage oscilloscope. Now from there we can find out what is the, we can give whatever is available, whatever frequency is available to us. Say 50 hertz supply we are giving, so this is 50 hertz. Now we can measure from DSO what is the phase displacement, or because it is time that the DSO there will be some divisions, horizontal divisions. It will be written some, say, uh, whatever, some time per division, so say some k millisecond per division. So that means this division, horizontal division, means k millisecond. I am just indicating something. So using cursor, you can you can you can put two cursors here and measure what is this time by which the current is lagging the voltage. So you know the time t, say td, by what, by by that much time duration the current is lagging the voltage. If you know the frequency, you can convert this to angle, right? So you can, whatever, 2 pi into 50 into tau into td, that comes out to be the phi angle, that is the phase displacement between the voltage and the current. And this phi angle, so td already you can measure from the DSO. So you know you are applying 50 hertz, so you know what is the phi angle that you are having between the voltage and the current. And if you have a series RLC circuit L and R, there will be no for induced EMF, because there is no field winding current, so there will be no induced EMF in the armature. So the effective circuit is like RL circuit with some sinusoidal voltage source. So you know from phasor analysis, you know that the voltage, if this is the voltage VA, current IA will be lagging that by some phi, and that phi will be, so tan phi will be omega L by R. So omega already you know, this is 50 hertz, so 2 pi f, and R value you have already measured from the DC resistance test, and so you know you have measured phi also. So from this you can put the values and find out what is the inductance value of that winding. Similarly, the similar experiment you can do it for the field winding also. You will measure the voltage of the field winding, current of the field winding. Same thing is expected. You expect You expect the field winding current also to lag the field winding voltage by some time. You measure the time, you convert it to phi, the phase displacement. You know that the tan phi is nothing but omega L by R, where R in this case is the field winding resistance. So you know everything, you know omega, you know phi, you know RF from the previous experiment, so you get what is the LF. So by these two methods you can get the armature and field winding inductance. One using the transient one, that is a step response. You give a step, you need a voltage source, DC voltage source, a switch, you suddenly turn on, you get the response, the rise of current. You fit it to a first order response, you get time constant. From there you get inductance because you know resistance. Second thing, you excite by some sinusoidal voltage source. You measure the phase displacement or the time displacement. Then from there you get the phase. uh, Again, you know tan phi, tan of that phase is omega L by R. You know what frequency you're exciting with, so you can get the LF. Okay, so field winding resistance and armature winding resistance both you have got. Any question here?
It's clear, sir.
Okay, now next we want to get the back EMF coefficient. That is, we have written back EMF is equal to K into IF into omega, right? And if we get this K, the same K is applicable in the torque equation also. So now what do we have? We have the motor. So actually we need to the pump will not work here. So whatever is the load, we have to actually disconnect the load and connect another motor here that can that can drive the first motor. So say this is the motor under test UT, and this is a driver motor. So this is going to drive the motor under test. So we have some way of driving this whole motor assembly at a constant speed, say omega. We have some procedure doing that. We have the field winding, we have the armature winding. We will keep the armature winding open and we will measure whatever is the armature winding voltage, right? And we'll be connecting some DC voltage source here. We'll be connecting some DC voltage source here, say VF. We will a variable DC voltage source. Let us say we can so that we can control the current. We can change the current that we are injecting into the field winding, right? Now if I remember whatever is the armature winding KVL equation, LA DIA dt plus EB. Now in this case, because the VA is open, or the armature winding is open, so there is no current. So the current flowing through IA, that is equal to 0. So this term Ia is equal to 0, so this term goes to 0. This Ia is constantly at 0, so dia dt, that is also 0. So there is no resistive drop, there is no there is no inductive drop. So whatever Va we are measuring, that is same as induced EMF, right? So now what do? We again plot something. We inject some current, we inject some field winding current. So this x-axis here is field winding current, this is the induced EMF. This is also known as the OCC, open circuit characteristic. So that relates the induced EMF and IF at a particular speed. So say that is rotating at say omega equal to omega 1. We change the IF. We start with uh, 0 if, 0 if also you will get, because of initial magnetization there may be some small voltage, and after that you get different points, and you will see that after some value of current the voltage will not rise at the same rate, so that will be due to the saturation. So finally you will get some curve like this, where in the mid portion this will be majorly a straight line. After that it will bend like this, and initially there will be a y-axis intercept, that is um, due to the remnant magnetic flux in the motor, because of which even if no current is there, there will be some, because of the as the motor is rotating, and there is some remnant magnetic flux. So because of that, some small amount of voltage may be there in the in the in the armature winding. But from there you can get what is the slope. This slope will be EB by, so delta EB by delta IF. So from this equation, delta EB, so EB by IF, so you get K omega, and you know what is the omega at which you have operated the motor. So this omega is also known to you. So K omega is nothing but this slope delta EB by delta IF, that is equal to K into omega. You know what is the omega equal to omega 1, you have run the motor at, so you can get K equal to 1 by omega 1 delta EB by delta IF. So this is the K value, how to get this K value. And just to avoid any uh, just to average them out, you can also run the motor at another speed, say omega 2. If it is higher, you will get something, some curve like this, right? You can get some more curve. So this is at omega equal to omega 1, this is equal to omega 2. You can get the second value of K is equal to 1 by omega 2 delta EB by delta IF. And mostly these two Ks will be quite close to each other. If you want, because there will be some experimental errors, some data equation errors, any experimental measurement you do, that is there is some error in that. So if you want to average them out, you can do the same experiment at multiple speeds, and then you can record the linear region, you can record the linear region slope for all those cases, and you can divide the slope by the omega, the speed, and you can find the K values, and you average them out. So say omega 1 you have find some K1, omega 2 you find some K2, omega 3 you find some K3. After doing some experiments, you take all these K values and you average them out. That is what is the most acceptable experimental procedure. Whatever measurements you do certain or you do a number of experimental measurements, and you average them out too, so that the experimental errors, they also get averaged out. Okay, so this is how to get the back EMF coefficient K, this coefficient, and that is same values, the value will be same, that will be appearing in the torque equation also, K into IF into IA. So the numerical value will be the same, but the units will be different. So this is, you have got the back EMF coefficient also. Now let us discuss about the mechanical system parameters, that is, we need to know what is the J value, what is the moment of inertia, and what is the B, what is the frictional coefficient. Now to do that, what you can do is, still you have the motor. Now earlier you needed some driver motor to drive that one, because this motor alone will not generate any torque, because we are keeping the armature one open. So this motor is not able to run at certain speed, but this driver is running the motor and taking it to some speed, and you are measuring the induced EMF. But in this one, we will not connect any load one. This is a no load test. No load test means there is be no load, no mechanical load or generated load connected to the DC motor. This motor is anyway grounded, or that is connected to a fixed support, bolted like that, and you have the armature winding, and you have the field winding, right? So in this case what you will be doing is you will be injecting some field current. So say you inject the rated current, say 1 ampere, whatever is the rated field current, you excite the motor with that, and you keep on, you run the motor at different speed by varying the armature voltage. So what you do is you run the motor at different speeds and measure what is the voltage VA that you are applying and what is the current that you are injecting, right? So you make a table like this. So VA, IA, omega, right? This is serial number 1 2 3 4 5. So the first, say you give VA1, you measure that IA1 current flows and there is some motor runs at a specific speed, say omega 1. Then you change the armature voltage, armature currents also change, and you get some omega 2. All this while IF is fixed. And then VA3, IA3, omega 3, VA4, IA4, omega 4, VA5, IA5, omega 5. So all these cases you got. Now uh, what is the loss that is happening? What is the loss that is taking place in the motor in this case? The armature circuit, because field winding circuit we are not measuring the voltage and currents, we are just fixing the current, so the field winding loss is not included in that. Anyway, the power transfer happens from the armature winding only. So the armature winding VA is equal to IARA plus LA DIA DT plus EB. So that is the transient equation. Now because you are operating under steady state, so that means your IA and VA, those are constant DC quantities. So the steady state equation is VA equal to IARA plus EB. So you note that this goes to 0 under steady state. Now because you already know what is the RA, the armature circuit resistance, so what is the total power? So if you multiply both sides by IA, that is the current, so VA into IA equal to IA square into RA plus EB into IA. So VA into IA is the input power, this is the I square R loss or copper loss, and this is the power, so mechanical power which gets converted, so mechanical power converted from electrical power, right? So but in this case motor is running under no load, so that means it is not driving any active load, and whatever power is being converted from electrical to mechanical, that is only required to oppose the frictional torque. So this in some sense EB into IA in this case under no load, this is a measure of frictional so power loss due to friction, P friction, right? So how can you get that? For all these cases
Sir,
you can
how we can
calculate
say
this.
that you are saying EB into IA is complete loss due to mechanical, right?
Yes, so
It
this is
will
the
be
complete. So if the motor will be driving some load, this will be the complete mechanical energy or mechanical power that is converted from electrical to mechanical. Now you come to the specific case, is there anything connected to the motor?
no,
It is
no
not
load
driving
is
any torque,
connected. No,
no
no.
load is connected, so that means it is this amount of power is only due to the friction or core losses. There will be some core losses also in the DC motor, which is anyway quite negligible. uh, for all practical purposes, the core loss can be neglected, and on the whatever EB into IA, the power other than power loss, other than the copper loss, that is mostly due to the frictional torque, or the to overcome the friction, because there is nothing else other than this. There is no load connected. Had there been a low generator connected or a pump connected, then this EB into IA would be total mechanical power. That will be total mechanical power would be EB into IA. Part of that will be friction, and part of that will be load. But in this case, because P load is 0, there is nothing connected, so whatever EB into IA we are having under no load, that entire thing is pre-frictional if we neglect the core losses, which is anyway fine. Right? Clear?
Clear, sir.
Okay. So for all these cases of experimental measurement, you can basically calculate this P friction is equal to VA minus IA square into RA. You know VA and IA for all of them. RA you have already estimated. So you get some values. You get some values for all these cases. In order to get the torque from the power, so the frictional torque, T friction, what you do? You divide the power, frictional
By
power, by
speed.
omega. Yes. So you get the frictional power, frictional torque also. Now if you plot x-axis as omega and this as frictional torque, you will find all these points. So this you need to plot these points, and you will find that there are some points like this. And most cases, if you join these points, you will find that it is a straight line joining so going to the origin. So this slope is nothing but delta T friction by delta speed, that is equal to B. That is the frictional coefficient, right? So you found the frictional coefficient also. Now to get the J, what do? Say you keep on measuring speed. You get some measurement of speed, okay, and uh, you run the motor up to certain speed. So if you see the speed in oscilloscope, the omega will look like this. Omega, it is at certain speed, omega 1. Now you suddenly disconnect this one, so that immediately there is no torque. So if there is no torque, so at this point it is disconnected, it will fall. It will fall exponentially, right? This is how the motor speed will fall. And if you so this is again assuming it to be that first order linear system, Te equal to J d omega dt plus B omega plus TL. Anyway, there is no TL load torque here, so Te equal to J d omega dt plus B omega, that is our system. So Te suddenly goes to 0,
Sir,
where
could you please
initial
repeat?
condition, uh, which
From when we
uh,
removed the current supply, the torque
yes.
will fall. That's fine. From that, could you
Okay.
please continue?
Okay. Okay. So if we disconnect the motor or the supply, then the torque will fall to 0 immediately, because if you open the circuit, current is 0 instantaneously, so that means the torque is also 0 instantaneously, right? Or not exactly instantaneously, but with respect to mechanical time constant, it's almost instantaneous. So after that, what will happen? The speed will fall. So if we look at the equation of mechanical circuit, TEM equal to J d omega dt plus B omega plus TL. Anyway, there is no load, so our equation is TEM equal to J d omega dt plus B omega, right? So now at this instant, now before this instant, what was there? Before this instant, in this duration, J d omega dt was 0. So whatever TEM was being supplied, that was used to overcome the B omega, that is the frictional torque. Now after that, in this duration, at this instant the Tm suddenly goes from whatever value it was, from there it goes to 0. So our differential equation becomes 0 equal to J d omega dt plus B omega. Now this is a differential equation with the value of omega at whatever t equal to t1, say this instant of disconnection is t1, that is equal to omega 1, where this value is omega 1. So you can solve this differential equation, you will get the fall of omega as t is equal to the initial speed omega 1 into there will be exponential fall tau t by tau mechanical. So this is assuming this as the 0 instant, or otherwise you will have to have t minus t1, whatever. That is only about time shifting and other things. You can solve this differential equation and get that, but main important thing is this is an exponential fall, and it will be like this, it will be falling exponentially like this. If you look at the speed in the oscilloscope, you can get how it falls. From there you can calculate what is the time constant by looking at the time duration, but a better way is to look at the initial slope. The initial slope also can tell us important things. So easiest way, neglect the nonlinearities. You get the falling time period, you get the falling period, and divide by 5 approximately, and you get the tau m, the mechanical time constant. And mechanical time constant is nothing but J by B. You already know B from the no load tests. So you know Tm tau m, the mechanical time constant, from this deceleration test. So you can calculate what is the polar moment of inertia for this motor. So all the parameters of the motor. Another alternate way could be, if you know torque, if you know how much torque you are applying. So if you suppose, let's really raise some portions. So say you can estimate torque quite well. So torque was initially at some value, initial Te1. So Te1 was the initial value, and motor was rotating at omega 1. Now because you can change torque quite fast, so you increase torque from Te1 to Te2 in an instant by just giving a step change, or by increasing the current quite fast. Now current will take some time to rise, but that time, in mechanical time window, in time window relating to mechanical time constant, which is in seconds, that rise time will be negligible in the torque waveform, so it will appear as almost a step change. And this omega, it will also rise from a speed, initial speed of omega 1 to omega 2, and it will rise like this, and you can find the time constant from here also. And so one could be through acceleration test, where you are using a torque pulse, or torque step change in torque, or it could be from deceleration test, where you are running the motor up to certain speed and suddenly disconnecting the supply and allowing the motor speed to fall, where you are observing the motor speed, and that from there you are finding out the mechanical time constant. Anyway, both of them should be reasonably the same. Um, so You can find out the mechanical time constant, and you can find out the J, the polar moment of inertia of the motors. Okay. Now in deceleration test there is one thing, because very close to zero speed there will be some, so there will be some non-linear friction very close to zero speed. The whatever the frictional coefficient as constant that you typically get, that is not very true at very close to zero speed. So here you can assume that if you solve the equation, if you get exponential decay, so that means it will decay exponentially, and it will take infinite time ideally to decay to zero. But in the practical cases it will decay, and when it reaches that very a certain speed very close to zero, it will stop. It will not rotate at a very slow speed for infinite time. It will simply stop, because there are practical non-linearities in any system. So deceleration test, yeah, um, it's a little bit tricky. So if you are fitting the exponential decay type of a plot in the experimentally obtained one, you have to fit it within some window. You cannot fit it up to the time where the speed comes to zero, because very close to zero speed there may be some non-linearity which may distort the actual curve from the ideal one. So it is better to take a window like this, a, a narrower window, where you will be trying to fit the experimental curve by this analytical one, and you can get the mechanical time constant. And once you get the mechanical time constant, you can get the moment of inertia also. So thus we got the resistances uh, through DC test. Then we looked at two methods to find out the inductances, one by giving a step change and measuring the time constant, another by exciting with AC voltage and measuring the phase difference. Next we looked at the how to get the back EMF coefficient, the no load test, or the OCC, open circuit test, open circuiting the armature winding, giving some field winding current, running the motor at a constant speed, and measuring the induced EMF. Doing it for multiple speeds, we can get the K, the back EMF coefficient. Next is the mechanical subsystem. We can do no load tests, run the motor under no load for different cases, measure the input voltage, input current, and speed, runs such similar experiments. We can get the frictional torque, frictional power, we can get the frictional torque, we can plot the frictional torque with speed, get the slope, that is B. Now we can do deceleration test or acceleration test. Deceleration test, we allow the motor to run up to some speed, and then suddenly we switch off the supply and record the fall of speed of the motor, and try to fit it by this first order falling curve. We get the mechanical time constant, we get the J from there. Next, there is a possibility of doing acceleration test, where we apply some torque, say T1, we apply some second torque T2, we record how the speed goes from omega 1 to omega 2. We can get the time constant from here. Once we get the time constant, we can get the J. So let us conclude it here. So we have completed dynamic model of DC machine. We have understood about the parameters. We have looked at how to get the parameters if we have a practical DC motors. Any question?
Sir,
Not
if you
let us.
have
Yeah.
Ekeshani, a good version of it, please share us, sir.
Okay, I have something. I don't know whether that is. Okay, I'll share whatever I have.
Okay, sir. Actually, I have downloaded a copy, but in that The printing of the letters is not good. It is difficult to
Actually, I
go
also
with
I
it.
also have the same one only. I also have the same one where the letters are quite thick and it is very difficult to understand. Yes.
Yes, sir. Yes, exactly. I'm facing the same.
Okay. Try to get something else.
Okay, sir. Okay. Thank you.
Okay. Thank you. Good night.